All right, so I guess we'll go ahead and get started. Thank you for everybody who showed up at 8 a.m. You guys were great. My name is Rosie Cook. I am the assistant curator at the Chemical Heritage Foundation here in Philadelphia, and I am sort of the organizer of this program that we have this morning, which is entitled Instrumentation and Innovation, a Personal History of Instruments and Innovation. We have 3 speakers today, including myself. The first speaker is going to be Dr. Baird, right here. He is a historian of science, and he's the provost at Clark University in Worcester, Massachusetts. Our second speaker is going to be David Brock. He is also a historian of science and is a senior research fellow at CHF with myself. I'll put the plug in now early. If you like the history of science and you like museums, please come and see our museum. We're located at 3rd and Chestnut, right next to Franklin Court in Old City. We're open until 8 p.m. All week, Monday, Tuesday, and Wednesday. So please come by, have a peek at our museum. We also have our Hall of Fame booth, which is down all the way on the other side at the Broad Street lobby, which features a bunch of instruments from our collection. So without any ado, we will bring Davis on up here. There we go.
Thank you, Rosie. Well, I'll start with a half a correction, which is I am a historian of science, but I'm also a philosopher of science. And the talk, in fact, is going to be a kind of amalgam of history and philosophy and also maybe a bit of journalism. I'm going to play on the pun in my title, which is to say Engineering Realities. How do we make this go forward? There. Okay. I got it. Oh, look at that. Here we have a phrase that can be treated in 2 ways. Engineering as a verb. Here we are, as it were, controlling our constructed worlds, our technosphere, if you like. And I'm going to talk a bit about what it means to try and control and construct these worlds through engineering. But engineering realities could also be part of a noun phrase. What world, or better, worlds, does a newly engineered product enter? And how do these worlds then shape the product? And the story I'm going to tell will play back and forth between both of these readings of engineering, and I'll try to be clear which way I'm reading at different points. So let me start with engineering-verb realities. So I think the simplest way to capture what we're trying to do when we're engineering verb realities is to control through designed artifice. So we build things that are designed where we have intent to control things. I think that's probably the shortest, simplest nugget of what we're trying to do, and really what I'm going to look at is how this simple idea gets much more complex when you look at in context, as it were. I will, as I would say, complexify it. And I'm going to do this by looking in a little detail at one company. The name of the company is Ometric. Various contributions to engineering reality. Ometric initially aimed to produce instrumentation that would be useful for quality control in pharmaceuticals, so to say, perfect pills. And I will say something briefly about the use of certain pharmaceuticals for people, since we are the consumers of these pills, so to make perfect people, so to say. And finally, there we go. I'll talk a little bit about the technology that is Ometric's IP, so to say, superior spectrometry, if you will. But engineering realities, noun phrase now, Ometric developed some very interesting, in my opinion, IP, but it had to enter a world where this IP would have some value to the markets it was trying to enter. And it had to create interest in its product, awareness of its product. It had to situate the product amongst alternatives. Typically, these alternatives all have financial issues tied to them. So there's a lot about the engineering reality that Ometric was living in that had an impact on the actual IP that Ometric was. And the other piece of this that I actually am very interested in is how Ometric, which came out of the University of South Carolina, was developed by a faculty member in the chemistry and biochemistry department there, how Ometric was related to the university. And at this point, a personal aside, I was for many years a faculty member at the University of South Carolina. I know these people, the principals involved, while I'm now at Clark University. During most of the history of Ometric, I was actually almost actually a player. So this is not quite disinterested history, if you will. Ometric begins, at least formally speaking, when its inventors, but the primary inventor, Michael Myrick, chemistry professor, applied for a patent for multivariate optical computing. The patent was filed in 1997, awarded in 2002. In general, it provides for a way to optically filter light so that the output of the filter mimics an analytically designed multivariate compression of spectrometric analysis of light. I'll talk a little bit more about that later. I suspect some in the audience will know more about that than I may know about it even. Although, as another aside, my first work in the history and philosophy of science was on the development of factor analysis, which was used initially to measure intelligence. It's a very similar statistical technique that Ometric is using, in fact. Between the time that Mickey developed the idea and Ometric, he tried himself to interest mostly pharmaceutical companies in the value of this way of doing quality control. So for a bunch of years, 5, 6 years, he was spending time trying to interest people without much success. And he was a little frustrated by this because, well, like any faculty member, he thought his idea was great. And I think it is a great idea, but he was not getting a lot of interest. Around 2003, 2004, a man named Jason Williamson, who was a young man looking for entrepreneurial opportunities, found his way to nanotechnology and Mickey Myrick. And here's where I actually have a role. At the time, I was leading a group of people at the University of South Carolina looking at societal implications of nanotechnology, whatever that might be. And we had started a South Carolina Citizen School of Nanotechnology, which aimed to present to a very diverse audience some of the interesting aspects of nanotechnology. And Jason was one of our first quote-unquote students, and it was through that experience that he made a connection with Mickey Myrick. In October of 2004, he and his partner, Scott Means, licensed Myrick's IP, and they formed Ometric. USC took an equity interest from quite a modest upfront payment from Williamson and Means. They applied for and were successful in getting a modest venture capital from the only, at that time anyway, venture capital firm in South Carolina, the Trellis Fund. They got an SBIR grant. They got their first commercial buy from GlaxoSmithKline. It was also modest. A particularly important move was they hired Walter Alessandrini in April 2005. Alessandrini was important because he was a retired entrepreneur at that time. I gather he was living on a boat in the Caribbean. He had just sold out a company called Avanex, which had gotten significant venture capital from Sequoia Fund. I'm sorry, this got cut off at the bottom. That was from a Mac to PC transition. And that was important because Alessandrini gave Ometric an in to the Sequoia Fund. So they got their second and significant venture capital from Sequoia thanks to Alessandrini. So the basic, what Ometric was trying to sell to pharmaceutical companies was quality control for pills. And basically what they were trying to say is you can, in real time, without delay, you can measure the pill content, as it were, of active materials for each individual pill, non-destructively, as it were, in time, real time. So instead of doing a batch analysis where you might produce a batch of pills, measure their quality content, and if it doesn't measure up, destroy the batch, here you do each pill and just throw out an individual pill. So to do this in general, and here's the sort of the philosophical piece of this talk, you have to identify the parameters you want to control. You have to find a way to acquire information about these parameters and decide on what are the boundaries that constitute success. As it were, this is a good pill versus failure. This is not a good pill. We're going to throw it out. Now, this is important because when you identify parameters, you identify boundaries of success, and you create a way to measure these parameters, you're making very significant choices about what of all of the things you could look at you're actually going to look at. As it were, it's the distance between what might be total control, I'm not sure really if that has any meaning, but engineered control. Engineering control says you have to look at specific parameters, come up with specific boundaries for success. And if you think about it, when we think about how we use pharmaceuticals for ourselves, for our now engineered bodies, it's the same story. We have to determine which parameters we want to measure, how are we going to measure them, and what's going to constitute success. And indeed, there are interested parties here, and anybody who reads around in the sort of the journalism around medicine and pharmaceuticals, there's a lot that goes on here that's actually, I think, interesting, potentially disturbing, although on the other hand, I am myself happily a consumer of many pharmaceuticals that keep me healthy, and that's true for most people these days. But it's important that the pharmaceuticals that I take are actually controlling the parameters that are important to me. In my case, it's my ability to breathe. Then there is this other interesting feature about pharmaceuticals and people. So ritalin, developed to control attention deficit hyperactivity disorder. But as you probably have read, it's widely used now by high school students because it can be shown that it raises their score on SAT significantly, 100 to 200 points. So we have a lot of unintended uses of this drug, which suggests that design itself isn't just in the mind or minds of the people working at the company doing the design. It gets distributed. We make a new product, we make a new instrument, it has what we think it will do, but actually in the end it's the broader world, the engineered reality it's entering that is going to decide how it gets used. So to say, design gets distributed broadly into the world. So just a tidbit more about what Ometric's IP is about. So you take analytical information from light, from a sample, Say you want to know percentage of active versus inactive material in a pill. So you do light analysis on these materials, and you get information from different wavelength bands of light. So you can do different kinds of spectrometry to get this information. And the history of these instruments is actually quite interesting. In general, the instruments are fairly expensive, and they're not very rugged, although they've gotten more rugged over time, but they're not very rugged because the optical paths involved have to be quite precisely controlled and so on. So the idea behind Ometric's IP, or Mickey Myrick's idea, is to analyze light responses in different wavelength bands and to construct what are called principal, that's P-A-L, components that carry the largest amount of information. So essentially, you look at which of the wavelength bands across the entire relevant spectrum carry the most information about the particular compounds or elements of interest to you, and you can construct what would be called the principal, or PC component, as a weighted function. That's what these alphas are, alpha 1, alpha 2, up to alpha n, of the different wavelength bands. And so that allows you, those alphas then are weights, so essentially what you do in the end is you construct a filter that weights the total amount of light by those wavelength bands, so you get a single intensity measurement instead of different wavelength bands. So you don't have to measure light by wavelength per se. You just have to measure the total intensity. It's quite simple, it's quite rugged, it operates in a very broad set of conditions. It can do it in line, so to say, in the production line in real time. So these materials, these light filters, control the intensities to maximally compress, so to say, the data that you're interested in. And this is important. So go back to the point, you got to know what parameters are you interested in measuring and what are the boundaries of success versus non-success. And you have to decide that up front. Based on that information, you construct your light filter, and then you put it in this equipment. Another nice thing about this, some people here may know that I have put forward an idea called thing knowledge, the idea that our things, or our instruments in particular, actually physically encapsulate knowledge that we have of the world. Well, these filters are a clear example of exactly that. Perhaps another point worth mentioning about this, I said it was principal P-A-L components, not principal P-L-E, and that's because these components are determined not from first principles, but they're determined empirically from an analysis of variation in the data. So you run a bunch of samples, you get a lot of data, and then you take that data and you do a statistical analysis. You compress the data to determine your weightings, your alphas, so to say. There's no background theoretical interpretation, although we may construct one over time. Okay, so that's some of the background to Ometric, what it was trying to do. Its initial idea was to create an instrument that would be of interest to the pharmaceutical industry, and it had to try and sell it to the pharmaceutical industry. And of course, what mattered to the pharmaceutical industry was how expensive would this instrument be? How rugged would it be? Will it actually save us money and save us, produce a better product for us? This was, so to say, the engineering reality, noun phrase now, that Ometric faced or entered as they developed their product. Their first big move, and I'm happy to say this here at Pittcon 2013, was a coming out at Pittcon 2006. And everybody here knows about the size of Pittcon, so I won't talk about that. Here are some images from 2006. That's Ometric in the display area. They, as it were, went in heavy. They didn't get a small booth, they got a big corner booth, and they developed a very large, big Ometric sign. This is for a brand new company that had, at this point, 4 employees. They hired a bunch of USC students to stage faux demonstrations in front of the convention center with signs that said something like, "We want real time," and so on. They conducted real demonstrations at their booth of what their instruments could do, but they also brought in, that the person in the middle there is now the late, I'm afraid to say, Andrew Sorensen, then president of the University of South Carolina. They made a big deal about this at Pittcon. They were curiously not able to interest a lot of pharmaceutical companies in their product, but they were able to interest dog food companies in the product. Dog food kibble, as it happens, the water content in kibble is very important. Too much and you have a mushy mess, too little and it just gets too dusty and falls apart. Dog food companies were interested in the idea of being able to control water content in their product. So that was the big success, so to say, of their Pittcon coming out party. But curiously, I don't know in the end, and it's something that I should know, but I don't right now, whether they sold this to dog food companies. Fast forward to about a year ago, and Ometric actually was sold or purchased by Halliburton, not for dog food, not for pharmaceuticals, but rather for the control of making cement used in oil and gas drilling, which is very important to Halliburton. This was a big deal in South Carolina. The purchase price is confidential, but it was significant, over 8 figures. The University of South Carolina itself received a royalty of $2.75 million, the largest royalty that the university has ever received. And what is also important here is that Halliburton only bought the rights, as it were, for multivariate optical computing applied in the oil and gas industry, which means that a new company was formed in April 11, Certimo. How do you spell Ometric backwards? Jason Williamson, you go back to the beginning, he's still interested in being an entrepreneur. He's continuing to pursue the use of multivariate optical computing and these multivariate optical elements, the filters, in other industries. And Certimo is happy to talk to anybody who's interested in that kind of quality control. And he purchased a worldwide exclusive perpetual license from USC to commercialize this, and he is hard at work at that now. So, by way of a conclusion, design through controlled artifice. This encompasses instruments, pharmaceuticals, people, well, oil wells indeed, businesses, universities, communities, et cetera, et cetera. You got to identify variables, construct metrics, establish boundaries. And in a certain very important sense, the reality that we get out of this is more than, in some sense of the word, reality, period. That's a nice philosophical phrase. In what sense? Well, it's more reliable, it's more predictable, it's more functional. We all prefer to live in a nicely controlled technosphere. But it is also less than reality because we're only measuring a certain relatively small number of parameters relative to the universe of different parameters we could measure. Full, so to say, reality is a richer environment than the finite list of parameters that an engineered reality can look at, and hence it diminishes that reality. And with that, I thank you very much for your attention.